You can see our vision pipeline here, where it identifies each piece, grabs it, knows which one it is, knows which bin to put it in because you told it to do that, and then it'll just execute on those instructions. And so we're really excited by this because this is like an example of an unstructured task, but also one that's instead of having to like manually program it, you just talk to it. And so it's very exciting. Robots heading in this direction.
All right, welcome everybody. Today's session is Vision AI for Robotics. We're going to be talking about how Almond uses computer vision to teach manufacturing robots how to handle some complex tasks. My name is Patrick. I'm from RoboFlow, and today I'm very happy to be joined by Shawn Patel, who is co-founder and CTO of Almond. Shawn, would you like to say hi and introduce yourself to everybody?
Yeah, hey everyone. Super excited to be here representing Almond and sharing how we use vision with robots, which is really fun and excited to share with all of you.
Nice. All right. Well, on that note, to give everybody some background, here on the screen, I have a few videos that I pirated from your website and put into the slide deck. I see some robotic arms doing various tasks. Shawn, for people who don't know about Almond, would you let us all know what's going on here and the work that you're doing?
Yeah, so our tagline is AI robots for manufacturers. So I'll break that down. We're targeting manufacturers. And so these are a few of the tasks that a lot of manufacturers do, like inspect products, maybe off a conveyor belt, move items from like a box to a bin or from a conveyor belt to a bin, which is pick and place. And then a big piece of that is machine tending because manufacturing is run by lots of machines in an assembly line. These bespoke machines need some sort of glue to connect all of them. And that's where we have humans today and robots tomorrow. And so we're helping fuel the transition to robots. And then the AI part is new in robotics, which is we're going from this notion of doing a lot of structured tasks, which is, a task that you can pre-program with fixed waypoints to tasks that you don't know where an item is until the task starts. And so you need AI to like find items, move them to different machines. Maybe you have two different machines that are completely different. So you need AI to be able to handle both of them. And so we're getting to a point where robots are able to do more tasks and become more useful because the AI models are getting a lot better.
Cool. Could you dive a little deeper into why AI for robotic arms in manufacturing? Like, I've seen robotics in assembly lines for a long time. If I'm a manufacturer, what does introducing AI unlock for me?
So I think the like biggest case of robotics in manufacturing has always been automotive, like you said, on the assembly line. And the reason why like traditional robots have worked really well on automotive assembly lines is because you're making a car like this very expensive product. And you have massive pieces, and every car, it's always putting its pieces in the same place pretty much. And so you can invest like a lot of money into robots because you're building a product that's so expensive. And that's why it's always worked. But when you think about like everything else that we use in day-to-day life, like nothing is nearly as expensive. And robots, especially fixed, really expensive robots, never really made sense in those tasks. And when you have a lot of different products and different product SKUs, you go from the notion of building thousands of one car to maybe like a few of like one specific item or like one specific piece of metal for like a metal manufacturer. As that brings the notion of unstructured tasks, where you need to be able to adapt to all these different SKUs because the heartland of especially American manufacturing is SMB manufacturers that don't like have $1 billion business, but maybe like a few $1 million or like tens of millions of dollars of a business. And these folks are building lots of products, not necessarily like super high volume of all of them. And so they want one robot that's affordable and able to handle doing many different things without having like heavy reprogramming costs. And that's where unstructured tasks come in. That's like the future of robotics.
You previously told me in the past, if you had a new task, you might need to like renovate your assembly line and kind of change stuff to accommodate the robot. Could you kind of tell me what you've observed there? Have you seen any examples of that?
So like if a manufacturer is using traditional robots and wants to like modify them for like a new line, first, generally they either have like automation engineers on staff or they hire out contractors to do this for like six figures, a lot more, usually like can be seven figures. to just reprogram. And this is not even buying hardware; it's just reprogramming the robot or like configuring their environment to handle a new task. And so that works well again when you're like building product that is going to generate a lot of money, and maybe you'll use that new configuration for like a year or like a few months at least. But most people can't afford that and don't really have that flow, and so it just doesn't work in that situation.
Cool. Here, I have a video that you previously sent me. It's an internal demo of a robotic arm handling an unstructured task in terms of high mix picking. I'm going to hit play, and I was hoping that you could talk through what is happening in this demo video for all of us listening in. So I will hit play now.
Yes. So high level overview, this is mixed bin picking. And so we're taking pieces of metal, analyzing what they are and sorting it. At the beginning here, you see this actually text to action. So you just speak into the interface how you want the pieces sorted. It parses the instructions, and then it actually identifies each piece. You can see our vision pipeline here where it identifies each piece, grabs it, knows which one it is, knows which bin to put it in because you told it to do that, and then it'll just execute on those instructions. And so we're really excited by this because this is like an example of an unstructured task, but also one that's instead of having to like manually program it, you just talk to it. And so it's very exciting. Robots heading in this direction where you can just talk to instead of typing out code.
You know, the first time I saw that video, I wasn't really thinking about it too much, and I kind of didn't appreciate at first how it's like, I was like, yeah, it's a robot picking up some stuff. But I think there's actually like a lot of complicated things going on there where, you know, previously, if you wanted a robot to pick up these different pieces of sheet metal, you probably would need them laid out, not lying on top of each other, right? So one of the cool things that you guys are doing there in that video that I like is it's like, here's just a random pile of stuff, and then we're going to teach the robot how to figure out which one is on top. Now that everybody has a little bit more context about what you guys are doing, and we saw that demo video, I wanted to shift gears a little bit and talk about your experience, you know, working with AI, computer vision, and then developing these solutions. So, you know, my first question for you is, would you tell me a little bit about your background? Did you have a lot of experience in machine learning or AI or computer vision?
Yeah, through school, especially, I did like robotics in high school. I didn't do robotics in college, but I built a car for Formula. But through those experiences, a lot of vision, a lot of machine learning. But this is certainly the first time of getting something from like just demos to production. And that's certainly the hardest part. If you're developing software, same thing, but especially with robotics, that is definitely a threshold that is newer to me. And so like trying to think about how to build computer vision from that mindset, it definitely changes how you approach it. Because you like are wary of, you know, like using open source, like zero shot models because it works great to do it once, but you know, it doesn't work great to do it like a million times. That reframing, I definitely learned a lot, and it's been like really fun trying to tackle that problem.
At what point did you know that computer vision would be playing a role in your solutions for robotic arms?
Yeah, so as some of the folks on the call might know that there's a lot of robotic startups being built right now, and that's because of two reasons. One, robot arms are becoming very cheap, and so you can now actually use them in many different situations. And two, there's the new notion of a VLA, which is this end-to-end model, which a lot of researchers have been researching for a long time, and a few companies are trying to put them in production, but they are yet to be in production yet. And so that was sort of like the culmination of Almond is we wanted to be part of this future of robotics with this new technology. As we started doing more of our own research and trying to deploy our own VLA models, we learned that like there's a lot of great research going into them, but it's simply too early, especially when we think about manufacturing tasks, and we'll dive into this later, but there is no 99% accuracy or repeatability. It has to be like 100%. And everything that's not 100% is like one failed part for a customer. And VLA models are not anywhere close to that. And so that's why we have to go to, you know, the tried and true computer vision, which we know works very well. And the great part about especially using things like RoboFlow is becoming even easier to use them and deploy them for different applications. And so that's when it was like, okay, we need to invest more in computer vision, and we need to figure out the best way to be able to train a lot of models, collect a lot of data, and use that to deploy to actual production use cases.
Beautiful. All right. As an employee of RoboFlow, I'm very happy to hear a little bit about that experience. At RoboFlow, we developed a family of object detection models called RF-DETR. And with these, the goal was to create like a state-of-the-art object detector that would give you like a really great trade-off between latency, performance, and accuracy. We've had a webinar about RF-DETR in the past, and we're going to have some other things coming up in the next weeks to explore the new model sizes we've released. But I just wanted to give a quick heads up there because we'll kind of mention this later and wanted to give everybody a bit of context. So with that said, Shawn, yeah, I really like what you just mentioned about there's some really cool cutting edge stuff in the VLAs, might not really be ready for prime time. So you decided to go back and develop a different computer vision solution. And one of my favorite things that you've told me about in the past was how you are combining different AI models together to solve one task. And on the screen here, I have some images that you shared. We have some model names, Grounding Dino, SAM2, stuff like that. Would you walk us through what we're seeing here and kind of what you're doing in terms of combining multiple models together?
Yeah, so this was the same use as that video we just saw. So sheet metals, figuring out which sheet is on top so you can pick it, and then identifying which piece it actually is so you can sort it. And so I just mentioned that you can't really use zero shot in production, but still that was the first approach we took, which was, can we actually get this model to work without any training data? Everyone streamed, but we took a stab at it. And so grounding Dino plus SAM is like a pretty common combo for zero shot object detection. So that was the first thing that we did. And the image you see with grounding Dino was basically the best we could do. It was able to basically cut out all the pieces of sheet metal from the larger frame, but it was not able to identify the sheet that was on top. And actually, with this combination, we had a depth camera on the robot too. And so we tried using the depth data to figure out, okay, since it's stacked, then maybe you can figure out using the depth data which one is on top. But the pieces were so thin and the data was too noisy that that was not really possible. And so we basically knew that we needed the third piece of the puzzle in order to actually solve this.
All right. And then could you tell me a little bit more about this is a later iteration of this pipeline?
Yeah, in order to go from grounding Dino, which was that general cluster of pieces, to the one on top, we failed at zero shot. And so we were like, okay, let's throw a little bit of data at this and see what we can do. And so the first thing we did was we did 50 samples we collected and annotated 50 images, putting a box around the top piece. And then went on RoboFlow and like I think we checked like every single model that was available, and we were just like, okay, which one performs the best? And RF-DETR was like the best by a lot from those 50 samples. And so then we just kept shoving more data at RF-DETR until it got really good. And it took less data than we thought, so that was nice. And then eventually we got a model that was able to perform like we see on the screen here of identifying the top piece. And then we still kept SAM in the picture just so we can do segmentation, because annotating segmentations is very annoying. But with the magic of RF-DETR, it made SAM a lot better. And so we still kept this whole pipeline by just shoving RF-DETR in between.
One thing I really like about this information that you shared here is there's a lot of great keywords here in terms of like region of interest, and then you're detecting an object, and then doing the instance segmentation and then classification. It's kind of like this is like a whole tutorial almost in different computer vision tasks. I was wondering, could you kind of walk us through like what are these different models doing in terms of, yeah, what does it mean to be finding that region of interest, and then what's the RF-DETR model doing, and so on and so forth?
Yeah, sure. So grounding Dino, basically, like I said, there's a huge image which probably shows a lot of what we saw on the table from the first video. And then grounding Dino just like finds the general area of interest. This makes RF-DETR perform better because it just filters out noise. And if we can do that with zero shot, that's awesome. So we were able to do that with zero shot. It runs very fast, and so we filter out the noise. And then RF-DETR now just basically has a stack of pieces of metal, And one, it's a lot easier to annotate this, and two, like I said, there's less noise from like basically anything else other than the metal. And so it's able to perform very well with what I thought was not a lot of data. And so that is awesome. And then, like I said, you could train RF-DETR to do segmentation, or maybe not RF-DETR, but at least some of the other RoboFlow models on segmentation. But annotating segmentations is not very fun, and very time consuming. And so SAM still is really awesome, where we're able to just take RF-DETR, segment it so we can actually find the exact piece on top. And this helps us because you might have saw it in that initial video, the robot is actually adjusting its rotation and position to pick up the piece, because on all of these, on this example, it's probably not so clear that you need to adjust rotation, but like, for example, you can have a piece that is like shoved against the side of the bin like this, but the robot will still be able to pick it up. And so the reason why we need segmentation is because if we're able to identify all the pieces on that metal, we can do some math and figure out what the angle is of the piece and then actually like move the robot to grab it. And so that's why we still need segmentation. And then VIT was very easy to train, just in terms of actually getting to know what type of metal it was. An interesting story here too was that with RF-DETR, obviously you can do multiple types of classifications, which was the first thing we did in order to do sorting. But we found that, interestingly, it was not performing very well on doing multiple classes of classification versus us just figuring out what the top piece is. But when we combined VIT at the end, which was the segmented piece of metal based on SAM, all of a sudden, since we're just detecting what the entire image is instead of a portion of the image, it performed insanely better with even less data. And so that was really awesome. And so I think it was just a really cool journey of combining a lot of models, and seeing that they all, do their own little things really well. And you can make something really awesome by combining all of them.
It's almost like a good example of the whole is greater than the sum of its pieces in a way, where by combining together these things, we get something that is more accurate and more reliable than just one model would have been on its own. Great explanation there. Since I talked to you about this a while ago, every now and then I do think about the segmentation part of, like a robot needs to know where the middle of an object is if it's going to grab it. And, I'm like grabbing a coffee cup every now and then, and I'm like, I know where the middle of this cup is and I can grab it, and I didn't even have to think about it. But this is something that we might need to train these robotic arms to do for us. Now, talking about accuracy, I wanted to move on down kind of and explore some other parts of model development. Before that, I'm not going to spend too long on this slide. I actually ended up presenting this at a webinar last week as well. But, in the past, I did some research where I was looking at, thousands of different models and data sets that were trained in RoboFlow and then kind of put into production somewhere. And when I was doing that research, I had this part where I was looking at over a 6-month period, examining how different organizations were retraining their models, adding additional training data, retraining. For example, we see here there's like a quality control data set that somebody had, and during that 6-month period, they added 10,000 images and they retrained the model 60 times, and then they improved the accuracy from there. On this chart, it looks like down at the bottom, they probably went from around 70% accuracy to maybe like it was like 90, 91% accuracy. So I wanted to talk to you a little bit and ask you a couple questions just about accuracy. You touched on this a little bit, but for different situations, accuracy means different things. Like I've seen situations where we're trying to catch defects in some kind of assembly line. And, maybe in the past, the items were going really fast and it was too fast for the humans to be able to catch all the defects. And then, they were only catching like 25% of them. So if you introduce a vision model and it's only 50% accurate or only catches 50% of the defects, it kind of sounds weird, but hey, it's still like a net gain and can be like a huge benefit to an organization like that. That's really different from what you guys are doing, I would say. So, first, I just wanted to ask, like, what does accuracy mean to you in a scenario where you're teaching machines, robots to do intricate movements?
Yeah, great question. And I think you framed it really well too. It really depends on what you're offsetting. And so all these robots are supplementing humans. And so when you're thinking about how well a human does, you need to basically be able to match that or do better in the robot world. And so, like you said, for defect detections, like humans probably don't get anywhere near 100%. And so robots or like vision models especially are able to do way better. In our case, like I said at the beginning, one of our core tasks is machine tending, which is basically taking pieces of metal and like putting them in a machine, taking them out, like sorting pieces of metal and putting them in different bins. These are things that humans are very good at, but they're still very hard for computer vision models to get very good at. And so accuracy is essentially very important and like the only thing that really matters in this case because like I said, when you're like putting a piece of metal into a machine, like a human is able to do that with pretty much 100% accuracy. And so the robot has to match that because there's you can't even exceed it, you just have to match it and be able to perform at that level. Otherwise, you're not delivering the right value to the customer. With the sorting demo, that's something where obviously humans can make mistakes with sorting, especially when there's a lot of pieces and they all look very similar. And so we're very happy with the results we got from here on RoboFlow in order to achieve that.
Now I was thinking about if you put me in front of a bin of sheet metal and it's like early in the morning,
Yeah.
and if you ask me to pick it up 100 times, would I successfully pick it up 100 out of 100 times? Maybe I'll need to test myself a little bit later to see what my accuracy is. You actually mentioned this a little earlier about you started off with like a small sample set, for example, RF-DETR object detection to train a model that would recognize which piece of sheet metal was on the top of the pile, right? You said you kind of started off with 50 images and then you continued to shovel more data into the model. Tell me about your shoveling process. What does that look like?
So we started with 50 images, and then from there it was like, okay, what do we need to do to like account for all edge cases? And so for us, it was basically like moving the pieces in different orientations and also lighting. Lighting is really big, especially with the metal. And this image, it actually looks quite good, but it was so insanely reflective that the lighting was like huge. And so we had like different lighting scenarios and we would collect data doing that. But mainly it was different orientations. Like for example, like you put a piece of metal like on the side of the bin or like different orientations, like different rotations throughout the bin by like changing the stack layer. And so that was a lot of the changes that we made. And then we just collected data from there.
Do you mind if I ask, like, what's your data set looking like these days? Do you got like a couple thousand images, and have you been labeling all of those by hand yourself? I'm kind of hoping that you have a little bit of like AI assistance on this task.
Yeah. So yeah, it's around like for this one, it was around 2000 images. That seems to be like the sweet spot for the tasks that we're doing. And no, so that's actually the nice part about starting small is that you shouldn't start in with doing 1,000 images because you have to label all those yourself. Like if you do 50, then you can use the 50 model to train like 200 and then use the 200 model to train like 500. And so the iterative approach is definitely the one to do here. It'll save a lot of time and you'll get the same performance. So yeah.
Nice. Yeah, I've been kicking around an idea recently of like model development is, it's kind of gone from human driven as like model as assistant, and now we're kind of going towards model driven, and the human is an assistant that helps and just reviews the model as it increases the number of images that are annotated and in that training data set. All right, so that wraps up like most of my questions for you. Shawn, do you have kind of anything else that you want to share with us that's going on?
Yeah, if anyone is interested in, learning more about what we do, or operates the manufacturing line and is interested in robotics, please reach out to me. I'm happy to chat. And also, if you're also generally if you're just working on any projects related to robots, so I was happy to chat with other folks in the community.
Nice. All right. Thank you very much for agreeing to come and share your experience with us. Been super, super informative, and I learned a lot about what you guys are doing and how to handle some different tasks. If you are watching this later recorded somewhere and you want to join us live at one of these webinars, please go to roboflow.com/webinar.
Yeah, thanks everyone for listening in, and thanks for having me, Patrick and James.